I'm really glad to have you on stage. This morning we talk about hybridization HPC with quantum computers. Now it's to find the way, can we have maybe one day a big quantum computers with a lot of qubits, logical qubits, to resolve the complex calculation? Or do we need to finally parallelize these quantum computers? And I think we can dive on this topic, and maybe there is not one response answer about that. Cathy, at IBM, what are the key challenges IBM face today in scaling a single superconducting quantum system to thousands of qubits?
Hi, thank you for having us. I know you guys have heard a lot today, so we'll try to be fun and quick, I guess. So IBM has obviously had a long storied history of building integrated chips in general. We've talked about scale, quality, and speed for a long time. The scale question is a good one. We have to build the physical scale. We've shown in our roadmap over the years that we can build up to 1,000 qubits on a single package. And we can also build very quality qubits in other packages like Heron and things like that. I think a key differentiator to our success is our cycles of learning. We're churning out a new chip with integrated learning, integrated information to get us more chips in about a weekly basis at this point. And if you look at our roadmap, we have like a very specific innovation roadmap that leads into our development roadmap. So I think it's an engineering challenge, definitely more than a scientific challenge at this point, but our cycles of learning are letting us continue to scale it at the physical qubit place.
Thank you. Georges, at Pascal, can we say that you have two challenges, that of switching from analog to gate-based, in addition to scaling the number of qubits? How do you see the next steps?
Well, actually, I think we have only one challenge. I mean, analog or digital, it's not a question, honestly, for the simple reason that with our technology, we can do both at the same time. It's exactly the same platform that we can use either in digital or in analog. So it's really not the challenge. The challenge, as you mentioned, is scaling the number of qubits while keeping the level of fidelity high enough to be able to correct the errors. And regarding this, we are facing all the challenges like the others. And we are building on the strength of our approach. We are leveraging neutral atom at Pascal. And to make a long story short, we don't need to manufacture the qubit. They are built by nature. So by nature, they are perfect, pristine qubits. And they are quantum at room temperature. So these are two key assets to scale faster. And in the lab, we already have thousands of atoms in our system. And second, maybe something which is even more interesting is the flexibility of this approach. We are controlling the qubits with light, and light is a fantastic tool that you can tailor to any problem if you want to. And very recently, we announced the fact that we bought a Canadian company which is specialized in integrated photonic on chips. So now a laser, which is big like this, is just replaced by a chip. And this is a key building block for us to scale to more qubits and FTQC. And last but not least, I think that neutral atom has demonstrated a lot in history, I mean in science, with a key breakthrough in the 90s with Bose-Einstein condensate, for instance. You can do sensing with neutral atoms, gravimeters, atomic clock, accelerators. You can build quantum computers, and last but not least, as it will be explained by Tom from Willink, you can also build quantum memories. And this shows, I think, the flexibility, and in an era where it's not clear which technology will be the winner, having the flexibility is a key asset.
Thank you, Georges. Tom, at Willink, you are proposing quantum memories that will allow several quantum computers to be connected to one another in order to scale the number of qubits. It's another path that we discovered recently. What makes this type of quantum networking attractive compared to promoting the very large, single very large machine?
Yeah, thank you very much, Fanny. So good afternoon, everyone. It's a pleasure for me to be here today. So as you mentioned, at WeLink, we are of course developing quantum memory, but above that, we are developing the entire stack of networking solution for interconnecting quantum computers. And I think the best strategy to move forward here is to push at the same time the performance at the level of the QPUs we can today build, but we are going to arrive in the short term to a ceiling of computing power we can reach at the level of a single QPU. And at this moment, we need to scale through networking. And it's, I mean, something which is already integrated in many roadmaps from many QPU vendors or also government or European institution, for example, where I think a good way to understand that is to look at what's happening around the world. If we are looking at tech giants like Cisco and NVIDIA, they are, as of now, incorporating networking into their roadmap for the deployment of next-generation quantum-augmented data centers. And also, we've seen very recently with IonQ recent roadmap announcement that key players in the ecosystem are now strengthening their positioning, consolidating the ecosystem, opening dedicated business units for networking, but also pushing the approach through acquisition from other companies. So I really think it's definitely a sign that the networking here is the most promising way to scale. And for me, it's not necessarily a debate here, but it's rather the question, how can we make Europe here leading this race? Because I think what we see today at this event is that we have a beautiful ecosystem in Europe with everything we need to make quantum computing successful. We have the quantum computing providers, we have the networking companies, we have the end users, and we have the data centers. So here, for me, the question is more, how do we make this a success within Europe? And I think here the best way to proceed is to help these different actors collaborate one with the other.
Thank you. Katie, IBM Quantum has a scaling strategy of its own, and you've made announcements this afternoon. Can you tell us about it?
We're very excited. I hope everyone, if you haven't got a chance to look at the press releases, I hope you do get a chance. But we made kind of the first detailed roadmap toward fault tolerance, and we will put a system online in 2029 that'll get us from the kind of thousands of operation range that we're in today to the 100 millions of operation to 100 million operations, which is why we're all here, right? We're all excited about what this means and what this is going to do for the technology, what this is going to do for the ecosystem. I think, this has been a culmination of efforts over time. And what's really important when you think about this kind of fault-tolerant thing, I think, one, it's important. Sometimes we talk about it in this esoteric space. All computation has errors, and we have to deal with them. And all of the devices that you have today are error-corrected in some way. And so we're taking a lot of that basis from classical computation, applying it to the quantum space. It's different and it's more challenging in some ways, but where we think we've announced today, what we know we've announced today is that we've turned it from like a scientific problem to an engineering problem. So there's kind of 6 main things that we announced today with proof that we have solved the scientific challenges with them. The system has to be fault tolerant, which means, like it says, it needs to be tolerant to faults. So we have to correct the errors more quickly than they accumulate. It has to be addressable, it has to be universal, and it also has to be adaptive. So we have to create the logical qubits, we have to be able to run the universal operations on them, and we also have to be able to adapt in real time the errors and correct them along the way. It also has to be modular and efficient. It has to be built in a way that is modular within a data center to where we can connect things quantumly, but it's also efficient that we can build these with underlying physical qubits that will allow us to run the algorithms that we want at a scale that's reasonable. So very exciting, like I said, years of kind of culmination of works. All of those principles that I just mentioned have been detailed to our approach and the science behind it. And we really feel like we've turned from science to engineering. Now, still a very exciting engineering challenge, as we all know. Lots to figure out in the next 4 years, where we'll be kind of building the architecture and laying it out. But really, the proof is there that we can do it now.
Okay. Tom, in the race of that, you promise to be able to connect quantum computers of different types, maybe photonics with atoms or others. Can you explain how this is possible? What type of quantum computer you can connect?
Yeah, sure. So the solution that we develop at WeLink for quantum networking are by essence multi-platform or hardware agnostic, depending on how you say it. And the reasoning behind that is typically, well, we build the network, which is an optical network, and then all the question is how we interface the various technologies of quantum computing to that network. And once you manage to do that, your network is typically becoming your standard here. And so at WeLink, we are developing the technologies that enable a variety of quantum computers to be plugged on that network. We are working, as of today at WeLink, on neutral atom quantum computing, superconducting quantum computing, and photonic quantum computing, with plan to expand these results to ion and silicon qubits as well. So one of the things I have to mention here is that, I mean, of course, we have access to these amazing technologies because we have pioneered this technology with our team at WeLink. But now, to go to the next step, it requires a very close collaboration with our partners, because now we are really thinking about how do we incorporate in the quantum computers the technologies that we are developing at WeLink. So this is something that we're currently working on. So that's for the engineering and scientific side. Of course, it's super exciting to see things advancing so fast here. But then there's also a lot of things we can learn from the business side when we think about networking quantum computers. Because when you manage to network quantum computers, you are actually drastically accelerating the time to market or the time to application of quantum computers. Because let's say you can stop at a number of physical qubits per chip, let's say a few thousand, and then you can scale horizontally. And so that's a way to accelerate time to application, but that's also a way for QPU vendors, for example, to be able to sell several quantum computers at a time. For non-QPU vendors, they sell one machine at a time, but once you manage to network them, you can sell 3, 5, or maybe 10 QPUs at a time. So that's also a way to expand the market, and we believe that's a very good way to accelerate all these developments.
Thank you. Georges Olivier, are you exploring architecture where multiple neutral atoms processor could operate in tandem, or would they coordinate them?
Absolutely. And again, it depends on what you want to do with this interconnect. Are you interconnecting cores to build the processor, or are you interconnecting processors because you want to add new functionalities to this? And the answer to this depends on your technology. If you want to circumvent, let's say, a scaling issue that you may have on a single core. As I said in introduction, with neutral atom, it's interestingly scalable. We are confident that we can reach 10,000 of qubit in a single core with neutral atom, and it's already working in the lab. I mean, not at Pascal labs, but in academic labs in the world. And with that, we plan to reach 200 of logical qubit with this system. And of course, you want to interconnect the processor later on, because as it was done in classical, you can extend the capacity of your processor. You can add more power, having more qubits if you want to. You can also add some security features to your system. Share the computing between different computers in a complete safety. And last but not least, you can also ease off let's say, the usage of a technology by itself, because you can share resources more easily. And this is what we are focusing at Pascal on this later stage, adding new functionalities. And as usual, we do that with our our application-centric approach. I mean, we want to turn scientific challenges into engineering ones. And if you want to do that, you need to be close to the applications. You need to be sure that the architecture you will find is scalable. I mean, industrially scalable. You can build it, and it can solve the real-world problem. And we do that with this mindset in partnership with WeLink. I mean, we are using the same atoms. Come on. I mean, so let's say the entry price is lower.
Thank you. Cathy, IBM has very good place into the quantum race, but isn't there is a risk of glass ceiling to the scalability of your qubit? Do you look at possible collaboration with other quantum computers?
Yeah, we collaborate with a lot of people on this stage. We collaborate across a lot of places. From the very beginning of the program, we know we're not going to do this alone. This is a great undertaking. We want to bring our strengths to the table and bring other strengths as well. So think about transduction in the future of how we want to connect these systems, all parts of the supply chain, cryostat, also the software stack. We've opened our platform for people to build on top, to build their own functions and their own interesting things on top of that. So we're all for partnerships. We want to build the technology fast. We want to get it into the hands of others. And we know that other people bring a lot of strength to the table to do that. And lots of connectors, as we've mentioned on the stage a few times.
Tom, can you give us your roadmap and the next technical steps, if you can?
Yeah, sure. So we can. So here we really, and it's not just WeLink. It's really, I would say, the ecosystem and the person who are working in this quantum networking industry. Really, our vision that I presented this morning is for WeLink to provide all the networking solution for the next generation quantum augmented data centers, where we'll deploy interconnected machine in data centers worldwide. And here, the roadmaps in the industry are aligned on the fact that we should be able to provide that by 2030, typically. So that's the objective here, to be able to deliver machine in this infrastructure which are network. And then how do we arrive here? Well, of course, you need to provide the network. We have built at WeLink this network. We have our solutions which are now available on market. We need now to build the quantum computer and to make the quantum computer, we say, interconnection ready. And this is something which is ongoing, is that we are advancing here with our partners. And once we have achieved these two, well, we can go towards deploying interconnected machine in this infrastructure. So that's, I would say, our main milestones here for the next-gen data centers.
Okay, George, last question for you. Pascal collaborates with WeLink and IBM, but on different projects. Can you explain what is the two approach in 1 minute?
In 1 minute, that's a challenge. Well, I saw that the new roadmap from IBM, and one thing which is not related to FTQC, because you can do something else than FTQC in quantum, is the fact that they also foresee that there will be a breakthrough, a quantum advantage with non-corrected qubits in the short term, in 2 to 3 years. That's the forecast from IBM. We have the same at Pascal. And this is not a bold assessment. I mean, we can say that because we have plenty of data. We ran some use cases, and we know what it takes to build classical solutions on these specific use cases. But first thing is that there is a path for the short term for quantum advantage. And we have this in common. And starting from here, we decided to join forces to deploy the technology, to show the market that there is indeed a quantum utility now, and that it's important to start working on these cases, because otherwise it will be too late. Think of AI, how fast it evolved in the last years. Everybody was left behind, and you don't want that to happen in quantum. So with IBM, we are working on that. So it means working on a unified software layer, because we want to offer the best of the two technologies to the market. So a unified software layer, and also working on a few use cases that will benefit from from both technologies, because they will not solve the same use cases. They have different assets, and by combining them, we can offer more. And this is what we are doing with IBM. With WeLink, it's more a hardware collaboration. We are working about the interconnect, defining the right memories we need, the architecture we need. So for us, it's a great way of addressing both the short term and the longer term, and let's say building the quantum computers step by step in a steady way and also in a secured way.
Thank you very much, three of you. I think we don't have one road to go to Rome, and this is same in quantum. We have many journey to discover how scaling or parallelizing the qubit. Thank you very much.